Let's get started. We have a small class today. I think people will trickle in. Or I wonder if people are watching the videos, although we haven't updated them recently. We're having trouble receiving them. Hopefully we'll receive them sooner, right? Okay, let's get started. Today we'll cover out-of-order execution. Again, this is one of those other fascinating topics that have preoccupied people for a long time in computer architecture. How to do this and how to do this very efficiently. Keep in mind very efficiently for a while because we'll get back to that. Today we'll cover the fundamentals. How does it work? How does it work efficiently is a separate question. What I will describe is not necessarily the most efficient implementation, but it gives you the fundamentals of how it works. But before that, remember that you have a homework. This is due next week, next Monday. And your third lab, now that you're done with the second lab and you're ready to actually do a pipeline implementation of MIPS, that's what you're going to do. So this is going to be even more fun. At some point, we should add the out-of-order implementation of MIPS to this course too, so you'll have even more fun, right? Now that'll be significantly harder. I guarantee you that. That's when you do a Verilog implementation, a gate level, synthesizable implementation of an out-of-order processor. It will take significant amount of time, but maybe at some point. There'll be 8 labs. Okay, and extra credit, optimized for execution time. This extra credit part will be easier than the previous extra credit. You don't need to do a complete redesign in this case, but you're going to optimize your design. So this should be fun. I'm hoping everybody will participate in this extra credit, so you'll have a competition, friendly competition. And maybe you can tell each other what's your execution time on some benchmark so that you facilitate that competition. Yes?
Right, yeah. Do we have a scoreboard or something so we'll know?
Oh, that's a good question. I don't think, so we will not provide that scoreboard, but you could do that on Piazza, I assume, right, Jungo? Is that? If you'd like to share execution times on some benchmarks, feel free to do so. But we're not going to have a mechanism, at least not yet, where you can submit your code and get the execution time. But feel free to create your own benchmark suites among yourselves and share the execution times. Don't share the code. This still holds. But the execution times you can share. That way you can motivate others to get better execution times too, right? Okay. Testing your code. I've talked about this before. Test your code well. Again, we're not going to give you all possible test cases. In fact, it's tough to do that. So test your code beyond the test cases we provide. We're going to test your code with test cases that we're going to create also. And this is part of life, right? That's how real life works. You got to test your code, regardless of whether you do software, hardware, or anything, right? Any design. You got to test it, make sure it works. Okay. Feedback sheet. This was due last Friday, but I would still like it if you haven't turned it in. So I'm not going to say no to you if you're going to turn in your feedback sheet to me right now. And I would really appreciate it, actually. This is important for me, important for you also, hopefully, in the course. And important for future generations, too. The course improves with your feedback. Now we get contradictory feedback also. And that's the nature of life also, because everybody has a different background and perspective. But we use these to improve the course, dynamically as well as in the next execution. OK, reading for today, we're going to cover, well, you've been reading this for a while, so you know that. But I'll give you some readings for next lecture also. Once we finish out-of-order execution, we'll look at some alternative execution models. And one of them will be SIMD, single instruction multiple data processing. We're going to talk about array processors, vector processors that have instructions that operate on multiple data elements. I briefly talked about this earlier, but we're going to go into more detail. And GPUs are an example of single instruction multiple data architectures of today. And a lot of you are interested in it, so I assigned 2 readings related to this. These are relatively high-level readings, but they should give you a perspective of what existing GPUs are like. And we'll go into more detail. And for next week, we're going to start the memory system, hopefully, starting next week. We've been talking about computation a lot, how to design pipelines, in-order execution, out-of-order execution, and these alternative models. But a very, very important part of today's systems is the memory system. In fact, most of the time, memory system is a bottleneck in execution. So we're going to look into a memory system for the rest of the course. And these are your readings for virtual memory. You've seen virtual memory before, but we're going to go into more detail, especially the hardware-software interactions, as well as the hardware implementation, hardware acceleration of virtual memory next week. OK, last lecture, hopefully you remember, we've covered state maintenance and recovery mechanisms. And there were 4 fundamental ways of doing this: reorder buffer, history buffer, future file, and checkpointing. And these are all applicable to in-order or out-of-order execution, even though we've described them in the context of an in-order machine, in-order dispatch machine with out-of-order completion of instructions, and multi-cycle execution. Well, multi-cycle execution is the reason why instructions complete out of order, right? But today we're going to do out-of-order dispatch, and as a result, anything can complete out of order. OK. And we've talked about interrupts, exceptions versus branch mispredictions. You know the difference, right? What is the key difference between those two? Yes?
Frequency at which they happen.
That's right. Which one happens more frequently?
Not the interrupt.
Not the interrupt. OK. That leaves, by process of elimination, that leaves branch mispredictions, I assume. Yeah. Branch mispredictions occur much more frequently. As a result, you need state recovery mechanisms that handle them quickly. Right? Because if you do not, then you're going to lose performance. But for interrupts and exceptions, you do not need state recovery mechanisms that recover the state very, very quickly. But once you have state recovery mechanisms for branch mispredictions, you can use them for interrupts and exceptions, because the fundamental thing is you want to go to a state that's precise. Right? OK. And we talked about handling register versus memory state, and keep this in mind again. We're going to get back to this when we talk about when we finish talking about Thomas Low's algorithm, out-of-order execution today. Register state is usually easier, as you remember. Memory state is harder, and there were 3 reasons why that is so. And I'll ask you when we get to that slide, hopefully. OK, today, out-of-order execution. So let's take a look at it. This was the in-order pipeline we were left with last time. If you look at this, at the end, we added a reorder buffer, or a reordering mechanism to ensure precise exceptions. The problem with an in-order pipeline, an in-order dispatch pipeline, and remember, dispatch is the act of sending an instruction to a functional unit, is that if you have a true data dependency, that true data dependency stalls the dispatch of younger instructions into the pipeline. Basically, you need to stall it at true data dependency. And we didn't have a mechanism to avoid this, right? Whereas we had a mechanism, if you had a false data dependency, we could avoid those by renaming, remember? And we did that, right? OK. So can we do better, basically? What is a true data dependency? I've given you a cooked up piece of code. Here, you have a multiply that writes into R3 and an add that reads from R3. And a bunch of independent adds. The blue ones are independent. The red one is dependent. Basically, these blue ones are actually independent of everything. This add is dependent on R3, this add. Basically, this add stalls the pipeline, so you cannot even put these instructions, independent instructions, into the pipeline, right? That's the problem. And the differences between these 2 pieces of code is one is a multiply and one is a load. Right? So what does that change? Well, I guess the first add stalls the pipeline, right? I guess I have a question here. What do the following 2 pieces of code have in common here? I'll answer the question. The first add stalls the pipeline, whole pipeline, in an in-order machine. And we'd like to avoid this. Why? Because its source register is unavailable here. And later independent instructions cannot get executed. I guess while we're at it, I'll do an aside. How are these 2 code portions different from each other?
The second one goes to memory, the first one doesn't.
That's right. And as a result,
It's probably slower. The memory one.
it could be slower, and it could be variable latency, right? Loads as we will see, it could hit in the cache or miss in the cache. As a result, it's variable latency, which means that its latency is unknown at runtime, until runtime, unknown at compile time. Again, what does this affect? Well, maybe a compiler can schedule around this multiply, assuming that multiply has fixed latency. Right? If it has always 5-cycle latency, maybe the compiler can find 5 independent instructions and place instructions before the add, such that you don't need to stall. But with load, it's a lot harder. And this is, again, one thing we've discussed fundamentally. So it's really with these variable latency operations, maybe we need to do something different than in-order execution. Maybe we can solve this problem in some other way in the compiler. If your compiler is really, really good, and if your program has those independent operations. Of course, you know that that's also hard, right? If your multiply latency is 5 cycles, and if you're fetching, let's say, 4 instructions per cycle, if you have a VLIW processor that is 4 wide, you need to have 20 instructions, independent instructions between the multiply and the add, and the dependent add. It may be very difficult for the compiler to find that many independent instructions to fill. So we really don't want to stall the pipeline when we get to the dependency. Okay, so how do we prevent this dispatch stall? I'll call this a dispatch stall. Dispatch, again, remember the act of sending an instruction to a functional unit. And the paper you're reading actually calls dispatch a different thing, but that's unfortunate. But let's use my terminology. And my terminology is common also, except the community is kind of divided in the terminology. Let's call it schedule. You could call it scheduling stalls also, but that's also, that could also be ambiguous, right? So there are multiple ways of doing it. And I will argue that you've already seen 3 ways of preventing dispatch stalls. Preventing a stall when you get a true data dependency. And I've already given you one way. I think I've given you the number 3 just now. The compiler somehow reorders instructions such that you never stall for a true data dependency, right? Either by inserting independent instructions that cover the distance between the producer and the consumer instruction, or by inserting no ops, or a combination of both. That way, you never stall on dispatch. What about the other 2?
Data forward.
Data forwarding, if you can forward, that's right, yes. That's one way of handling it. That's not what I had. I really want to prevent perfectly.
The multiple threaded thing.
That's right, yes, the multiple threaded thing. I'll give you partial credit for the thing. It has a specific name. That's good. Anybody remember?
Simultaneous multi-threading. Fine-grained.
Fine-grained multi-threading. That's right, yes. Fine-grained multi-threading. That's the first one here, probably. That's one of my favorite mechanisms, so it comes first here. The idea is basically you always fetch from some other thread. You fetch from a different thread every cycle, such that no 2 instructions in the pipeline from the same thread are present. Okay? No, you don't have 2 instructions from the same thread present in the pipeline. That fixes the problem. One more. And you covered this also. If you always do this, you never stall. Yes? Guessing, exactly, yeah. Value prediction, right? You guess the value. You need to verify it, but you never need to stall, right? Okay. Well, I'm not going to cover this, but there are disadvantages of the above 3. You may not be able to do this first. Fine-grained multithreading, you may not have threads, and you may care about the performance of a single thread. I guess I'm giving you the disadvantages. Value prediction, well, it may not work right. And people have tried to optimize this, but it's tough to do, right? At best, you get maybe 60% accuracy. And I'll let you imagine why you get those accuracies. For example, one reason you get good value prediction accuracy could be, again, think loops. Let's say you have for I equals 0, I plus plus. Well, I guess I less than something. And I plus plus. I guess I'll do a load here. I'll mix assembly and high-level language. And then add into R3. I guess this is really mixing it. Okay. dot, dot, dot. Okay, so this is in some register. If you look at this, this is really predictable, right? This I++ is really predictable. So anything that depends on this I++, you can predict nicely. If you have a stride predictor, I'll call the stride predictor. If you look at the values that this instruction takes, I++, this instruction produces, in the first execution, its value is 1. In the second execution, 2. Third, 3. Fourth, 4. Dot, dot, dot. Then the distance is constant between the previous execution. So you always add 1 to the previous value that this instruction produced, and you can predict this nicely, easily. Whereas, if you look at this, is this value easy to predict? R3? There's another dependency here, right? Which means, so you can easily predict this one, which means that you don't need to stall. And you're always correct. Well, hopefully always correct, except at the boundary conditions of the array. We would like to predict this value also because there's another dependency here, right? This load, we do load, and we do an add, and maybe we do some branch here, dot, dot, dot. The problem is this value is harder to predict, probably, right? Because we're loading something from memory. And now you're really at the mercy of what this array looks like. If this array, if you look at memory, this is the beginning of the array, and at A0, you have a bunch of values. If this array always contains zeros, or the same value, then this is easy to predict, right? You're always loading 0, regardless of what location you're accessing. But if this array contains random values, 2, 5, I don't know, imagine your favorite numbers here, then this is, you'll probably have 0% prediction rate here. So value prediction probably works for cases where things are predictable, and probably doesn't work for cases where things are random, right? If you're interested in this, actually, there's a paper that analyzes this in old programs, Sazadas and Smith. It's called The Predictability of Data Values. I believe it's in Micro 1997, but not perfectly sure. It could be ISCO also. But that analyzes values in spec benchmarks. And it has some interesting observations. OK. That aside, basically, value prediction has downsides also. And you need to recover, right? You need to verify and recover. There's that logic involved here, whereas that logic is not needed in 1 and 3. OK. Any other way to prevent dispatch stalls? I think the answer is obvious here. Basically, you've seen data flow, right? Data flow, you fetch and fire an instruction when its inputs are ready. Right? In a sense, it's a different execution model. You never need to stall. You always wait for your inputs to be ready, and you always have instructions somewhere waiting. That's the idea. So we're going to do that under the von Neumann model. The problem, the real problem is we have in-order dispatch, in-order scheduling or execution. And we would like to enable this data flow like dispatch. So we really want out-of-order dispatch, or what is called out-of-order scheduling or execution. This is also called dynamic scheduling, whereas in-order dispatch is usually called static scheduling because you're obeying the order given by the compiler. And the idea is simple, right? At its core, we're going to move the dependent instructions out of the way of the independent ones. So that's what's happening here, right? If you look at this instruction, it's getting in the way of these independent ones. We're not even seeing those independent ones. So when we detected this dependence, if we moved it somewhere else and recorded some information such that we could wake it up later, we would be able to put these instructions into the pipeline and execute them, hopefully. But we need some machinery to do this. So basically, we're going to take those instructions out of the way and put them into what is called the reservation stations. You could think of these as kind of like rest areas, right? if a car needs to stop, they don't stop in the middle of the road, right? If they do stop in the middle of the road, then we have the same problem we're seeing here. They go out of the highway and go to a rest area, for example. You could think of these reservation stations as rest areas for instructions that are waiting to do something. And they could be waiting for a data dependence in this case. And once we move the dependent instructions out of the way, of course, we would like to be able to execute them, which means that we need to monitor the source values of those instructions while they're waiting in that resting area. Right? So that we can actually wake them up when the source values are ready, because we need to be able to execute them. And when all source values of an instruction are available, which means that when they become ready, now we can fire or dispatch the instruction, just like the data flow, right? Remember the data flow nodes? When all of the inputs of a data flow node is ready, you can fire that and execute it. Which means that instructions are now dispatched in data flow order, right? When the data is available, the instruction gets dispatched. It can execute. What is the benefit? Well, this gives us now latency tolerance. Basically, we're moving the dependent instructions. It allows the independent instructions to execute and complete in the presence of a long latency operation. Now, we'll get back to this, because if you do not have long latency operations, this is not really beneficial, right? And I'll let you think about that for a while. If all of the instructions are one cycle latency, then the values will be available, or you can make them available somehow, right? It's not as beneficial. Okay. Okay, so that's the basic idea. Let's see what it enables, and then we're going to actually go into detail with one example and see how it really works. So what does this enable? If you have in-order dispatch and precise exceptions for this cooked up piece of code that I showed you earlier, this is what it looks like. Basically, on the first add, you get a stall, because you need to wait for register 3's value to be available. And register 3's value becomes available after multiply executes here, right? And then you forward the data such that this add can execute right away. This is assuming data forwarding. And you also need to stall for this instruction, because this add is dependent on this previous multiply. It is also dependent on this previous add. Okay, but that value is produced there. So it takes 16 cycles to do this on an in-order machine, and you should be very comfortable producing this diagram. And this is assuming a reorder buffer stage also. If you do out-of-order execution, what we're going to do is, when we get to this add, the second add, instead of stalling, we're going to put it into this rest area where it will wait. It will wait until this multiply produces the value the add is waiting for. Multiply produces R3, basically, or this version of R3. And we're going to communicate that value and the fact that it was produced to this add while it's waiting in the rest area, and the add will start execution once that multiply completes. Right? But in the meantime, because this is waiting in the rest area, now we can actually decode the next instruction, because the pipeline is free, right? The instruction add has moved out. It's waiting somewhere else. Right? So you can actually execute this instruction, which is the second add, while the first add is waiting in the rest area. You can also, and that's independent, right? Because it's independent, it executes, and you write its value to the reorder buffer, and now it waits for retirement, for completion. And we can also execute the second multiply, because that multiply is also independent of any previous instruction. Right? And if you do this, well, once we fetch the last add, it needs to wait also, because its value is not ready, but it executes when its value becomes ready. So if you do this calculation, you actually get 12 cycles. Right? So it's significant benefit, right? It's 4 out of 16, 25% performance improvement. Yeah. Yeah. Well, that's assuming that you haven't lengthened the pipeline stages, right, by doing all of this bookkeeping. And that's something that you need to think about also right now. I'm going to assume that we're not going to lengthen the pipeline stages, but that's usually not the case. Because you need to do this bookkeeping here, some bookkeeping, move the instruction out of the way, record its dependencies, who it's waiting the values from. And when the value becomes available, somehow you need to wake it up. So you need some hardware data structures to enable that, and that could increase your critical path. So think about this. Think about the implementation of this. I'm not going to discuss that. I'm going to assume this beautiful picture that we're not going to modify the number of pipeline stages or the critical path in each pipeline stage. But that's usually not the case. An out-of-order machine requires longer pipelines because you need to do this bookkeeping. And what is that bookkeeping, basically? This should be revisited. Well, I guess it is revisited. I've given you the basic ideas. But let's be more formal about this. First of all, if we want this consumer instruction to wake up or fire when the producer is done, we have to somehow link them, right? We have to link the consumer of a value to the producer. How do we do that? Well, you already know how we do that. We'll get to that. Second, we need to buffer instructions until they're ready to execute. I already told you that. Third, instructions, while they're waiting in this buffer, they need to keep track of the readiness of their source values. And fourth, when all source values of an instruction are available, when the instruction is actually ready to execute, we need to dispatch the instruction to its functional unit. And there are mechanisms to enable all these four. These are the four fundamental things that you need to do. The first thing you've seen, right? How do you link the consumer to the producer? Register renaming. Register contains the value that is communicated between the producer and consumer. And once you rename the registers, you're basically linking the producer and the consumer. And we've seen ways of doing that, tagging, right? We renamed the registers when we did scoreboarding, advanced scoreboarding. And when we did the reorder buffer, right? We renamed the register entry to an entry in the reorder buffer. And we're going to rename the registers to the reservation stations today. But that won't be fundamental. It's really this namespace that we're changing that enables linking. You don't need to associate that namespace with a particular structure. You're changing the name. OK, how do you buffer the instruction until they're ready? Basically, we're going to insert the instruction to the reservation stations after renaming. And how do the instructions keep track of the readiness of their source values? Well, when an instruction finishes, produces a value, it broadcasts this tag that is associated with that value. And every other instruction that is linked to that tag that is supposed to get that value basically compares its source tags. And if the tags match, that means that this instruction is waiting for that value. Right? And source value becomes ready. Now we've linked the instructions here. Here we're exercising those linkages and ensuring that an instruction that's linked to its producer wakes or figures out that its source value is ready. Okay? And this is now easy. Once you figure out all your source values are ready, once all of the instructions source values is ready, instruction wakes up. And we're going to call it wake up. This is actually called a wake up logic in many processors today. And once you wake up instructions, there may be multiple instructions that are woken up. Well, then you need to select which one to send to a particular functional unit. Right? So this is actually out-of-order execution in a nutshell for you. It's simple, right? It's nothing sophisticated. The question is, how do you actually do that? And we're going to see an example. This is actually invented by Robert Tomasulo. At least this way of doing it is invented by Robert Tomasulo at IBM in the 1960s for IBM 36091. And it was used in IBM 36091 floating point units. And I'm going to describe how it's done in a way that's similar to that. But the fundamental principles today are really the same. The question is, how do you do it much more efficiently? And if you want to read the original paper, this is the original paper, an efficient algorithm for exploiting multiple arithmetic units. What is the major difference today? Well, this didn't take off at the time, actually. And we know what the major difference is today because I told you in the last lecture. It's really precise exceptions, right? This machine did not have precise exceptions. So things could complete out of order totally. And it was difficult for the programmer to debug that. Today, the major difference is we have precise exceptions. And these are the papers that actually advocated that in out of order execution. These papers actually led to the design of Pentium Pro. which was one of the first variants, one of the first high-performance processors that used out-of-order execution, the variants. There are a lot of other things in these papers also, but we're not going to go into detail in that. If you're interested, you can take 740 or 742. But the variants of out-of-order execution with precise exceptions is used in most high-performance processors today. And I don't think I can list more here. But pretty much all high-performance processors use it. Alpha 21264, which I'll recommend you readings for, IBM Power 5, IBM Z series. These have been traditionally in-order processors. Oracle, UltraSpark, it used to be Sun UltraSpark. ARM, even ARM has out-of-order processors today. And even MIPS, this is surprising, right? Because microprocessor without interlocking pipeline stages has out-of-order execution. MIPS R2000 was a very simple pipeline. MIPS R10000 is a sophisticated pipeline with out-of-order execution. Yes?
Does the without interlocking still holds true for nowadays MIPS?
No, it doesn't hold, of course. That was the goal when the MIPS architecture was designed. So it's the name of the architecture itself. But out-of-order execution is a huge form of interlocking, right? You actually keep track of where the values flow.
Also, does this still only have 5-stage pipelines?
No. I'll recommend you a paper. The MIPS R10000 architecture by Jaeger et al. Describes how out-of-order execution is implemented in this particular processor. Yeah. It's much more than, it's probably a 12-stage, 13-stage pipeline. And with all of the structures that I'm going to describe today. Actually, more sophisticated. Okay, so how do we do this? Basically, if you think of this, an out-of-order pipeline looks like this. An in-order pipeline, with precise exceptions, we added this reorder buffer, right? It had a hump at the end of the pipeline. Now we're going to look more like a camel with 2 humps in the out-of-order pipeline. Initially, pipeline is in order. You fetch and decode and rename instructions in order. And then you get to the first hump. You put instructions into the reservation stations scheduling window. This is also called the scheduling window. So there's a big scheduling stage where instructions wait for their source operands to become ready. And now the pipeline becomes out of order. Here, scheduling happens out of order. We don't obey the instruction ordering provided by the compiler here. And instructions complete out of order. They broadcast their value and tags to enable the execution of dependent instructions. And once they complete out of order, they write their results in order. They write their results into the reorder buffer, and the retirement is in order to satisfy the von Neumann architecture, right? Sequential semantics. So these are the 2 humps. You put instructions to the reservation stations, and then you need to do the reordering at the very end. We'll talk about this also. This is called the reorder buffer. It's also called the instruction window or active window. Basically, reorder buffer contains all of the instructions, the state or status of all of the instructions that have been decoded, but not yet committed, not yet out of the pipeline. This is also called the instruction window. You can think of the machine looking at a window of instructions at any point in time, right? Or the active window. Okay, and this, hopefully you read this paper. This is a general organization of an out-of-order processor from the paper that you've been reading. And I'm not going to go into this detail, but this is very similar to here, except it's a little bit more complicated. But you can see the reordering units here also, reorder buffer and commit. And these are the instruction buffers. These are the reservation stations. After decode, I don't know if you can see this. Like I point to it, but it's too small. After decode, rename, and dispatch is used differently here. You put the instructions into the instruction buffers, which are essentially reservation stations. And they wait their values here. And I don't believe that all of the connections were drawn in this particular picture from this paper, but you can imagine. Okay, so Tomasuo's machine was actually kind of similar. What they had was they had multiple functional units, floating point functional units, and they had these reservation stations in front of the functional units. When an instruction was decoded, you see the from instruction unit over there, it was placed into the reservation stations, and it waited for its values to become ready in the reservation stations. And when an instruction executed, it broadcast its value and the tag on this common data bus. And that if you look at this common data bus, it's connected to the reservation stations as well as the register file as well as the store buffer. And that once a value and tag are broadcast, instructions that are waiting for that tag capture the value and say, my source is ready. Okay. Let's talk about register renaming because it's an enabler of out-of-order execution. Right? And you've seen this slide before also. Basically, this eliminates output and anti-dependencies. You're changing the namespace from registers to something else. And you already know this very well. In an out-of-order machine, the register ID is renamed to the reservation station entry. I'm going to assume that for the example that I'm going to show you. Basically, register ID is mapped to a reservation station entry ID, where the producer of that value is going to reside. You can think of this as architectural register ID that's provided by the compiler, a destination register, and the physical register ID. Basically, physical register kind of resides in the reservation station. And after renaming, the reservation station entry ID is used to refer to the register. It's not R3 anymore. It's whatever reservation station is going to produce that value. Right? And again, it doesn't have to be the reservation station, but I'm going to assume that here. It could actually be anything, right, as long as you keep track of it well. Okay, this eliminates anti and output dependencies, and you know this already. It basically approximates the performance effect of a large number of registers, even though ISA is a small number. How large? Well, however large you can make your reservation stations to be. Right? It could be thousands, maybe, but we're going to see problems with that perhaps. Okay, so how do you do the renaming? You've seen this also. We're going to have a register rename table. Actually, maybe we should start having that on board at some point. Basically, we will have a valid bit associated with the register. And if the valid bit is valid, this value is useful, which means that the register file contains the value, up-to-date value. If this value, valid bit is 0, then this value is garbage, which means that it doesn't mean anything. But there's a tag here that says register 0 is mapped to reservation station entry X. Okay? I think I'll give you Tomasuo's algorithm briefly also. I'm not going to cover this because I'm going to go through the example. But basically, first you need to allocate a reservation station entry for an instruction. You get an instruction, you decode it. In the meantime, you try to rename it, but you also allocate a reservation station entry because you're going to move it out of the pipeline, right? And if available, the instruction as well as the renamed operands are inserted into the reservation station. Otherwise, you stall, basically. If there are not enough reservation stations, you stall. That's why you stall in an out-of-order pipeline. You don't have enough places. You don't have a place to place this instruction in the reservation stations. You don't stall in a dependency. You stall if the reservation station is not available. OK. While in the reservation station, I've already given you this. So we're going to look into this with an example. And when the instruction is ready, it's dispatched. And after the instruction finishes, it arbitrates for this bus. We're going to assume a common data bus. And it puts basically the tagged value on the common data bus. This is called the tag broadcast. We're going to broadcast the tag as well as the value. And register file is also connected to this bus. Basically, this register file or register rename table or register alias table as used, it's also connected to the bus. When instruction broadcasts this tag, this is actually a tag, that tag is compared to the tags inside the register file. And if there's a tag match, then the value is captured. That's how you get the up-to-date value into the register file. Basically, you have this register as a register value at multiple different places in the machine. Right? It could be in the reservation station. Some instruction may be waiting for a register tagged with that particular tag. And also here, the register file may be waiting for that value that has a particular tag. Right? So you need to view the registers as values rather than storage locations. OK, if the tag in the register file matches the broadcast tag, then the broadcast value is written into the register. And also, instructions that have the same tag set their source ready bits. At some point, you need to reclaim this rename tag. You need to reclaim the reservation station, right? So let's take a look at our exercise. It's best understood with this exercise, I think. And I'll use another cooked up piece of code to do this. But these cooked up pieces of code, remember, whatever piece of code you cook up, somebody comes up with it. That's a very good way of looking at programming. In fact, it's not terribly cooked up, right? You could imagine how this happens. But I'm not going to ask you to do the high level of that. So let's take a look at this code. It's not the same code that I showed you. But we're going to assume assume this pipeline. So actually, I'm going to assume imprecise exceptions for now. Basically, we're not going to have a reorder buffer, although it's trivial to add in the end. We're going to assume 4-cycle execute add additions. Basically, an adder addition will take 4 cycles, and a multiplication will take 6 cycles. This is actually the values that you had in IBM 36091. They wanted to have short clock cycles. And we're going to assume 1 adder and 1 multiplier. And we're going to look at how many cycles it takes to execute this in a 9-pipeline machine, although this is probably not interesting. Maybe I'll let you figure that out. And an in-order dispatch pipeline machine with imprecise exceptions, with no forwarding and full forwarding of data values. And an out-of-order dispatch pipeline machine with imprecise exceptions with full forwarding. And I'm going to focus on the last one, obviously. So this is the code. And you can look at this. I'm not going to draw this. I guess this is the in-order dispatch, right? Yeah. And with no forwarding. This is basically very basic scoreboarding. And you can see that if you have no forwarding, you start executing the dependent instruction after the previous instruction writes back its result into the register file. That's over there between the first 2 instructions. And it takes 31 cycles. If you do the calculation, it takes 31 cycles to do this. If you add forwarding, now remember the first instruction was a multiply, so it takes 6 cycles. And the second instruction is an add. It takes 4 cycles. After the first instruction finishes its execution, its result is available after 6 cycles of multiplication. You can forward that value to the execution unit of the add, and add can start execution. So you say 1 cycle here. And in the end, for this piece of code, you get 25 cycles of execution. So forwarding helps you a lot in an in-order pipeline. So how does out-of-order execution work? Basically, instead of, but here you still need to stall the independent instructions. If you look at the independent instructions here, these blue instructions are actually independent of this first red add instruction, right? So here, we still stall those independent instructions, but with out-of-order execution, we're going to get to 20 cycles. And let's take a look at how we do that. I guess I'll keep this over here. And go through the machine one by one for each cycle. I guess let me do this first. I'm going to draw this over here too. So what do we need in the machine? We have a register file, right? Actually, let's try to do the pipeline here. So we're fetching instructions here, and we're going to decode them. How do we decode them? Well, we're going to also access the register file in the decode stage. And this is, I'm going to call this the register alias table, RAT. And for each register, we have a val bit, and we have a tag, and we have the value of the register. Initially, at the beginning of execution, I guess how many registers do we have here? 11, right? Register 0 through, well, yes, let me do this. 1, 2, 3. Hopefully that's 11. Okay. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Apparently not, huh? Okay, now it's 11. Initially, all of the registers are valid, right? Somehow you load the context, and your context would better be valid. And you have, we're going to assume values, right? What did I assume here? Oh, 1 through 11. Okay. I'm going to delete this register 0. Assume that we don't have a register 0 here. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And these are our values. And tags, you don't care, right? Because the value is valid here, which means that the register is not mapped to any reservation station. It's already there. Okay. So once we decode the instructions, let me put the reservation stations here also. If you go back to this picture, we're going to have an adder. And we're going to have a multiplier. And each of them will have reservation stations in front of it. And I think for this adder, basically we'll have 4 entries. And we're going to name them as A, B, C, D, I believe. And you can correct me if it's not that one, but it is A, B, C, D, right? Yes. And for the multiplier, we're going to name them as X, Y, Z, T. Although we're going to use only X, Y, I think, for this example, since we have 2 multiplies. Okay. So what's in the reservation station entry? Basically, when an instruction is decoded, it's renamed. It renames its sources, and it allocates a reservation station entry, which basically keeps track of its sources. So basically, when an instruction is decoded, what it can do is it needs to read its registers. Let's say, what is the first instruction? It's a multiply, right? The first instruction is multiply. It's writing it to destination register 3 and reading from register 1 and register 2. It reads its sources, register 1 and register 2. And it goes into the reservation station, because we're going to move every instruction to the reservation station so that we can execute everything out of there. So what does placing an instruction into the reservation station mean? Allocating an entry for that instruction and copying the source register entries from the register alias table into the reservation stations. It's that simple, because that's what we're going to keep track of, right? In the reservation station, we want to know, this is the first source, this is the second source. Is the first source ready? If the first source is ready, what's the value? Then I can use and execute. If the first source is not ready, what's the tag? What's the tag I'm waiting for this source to become ready? Well, it's the same thing as this one, right? Valid tag value. When you decode the instruction, the first register, it's valid. Its tag, you don't care, because it's valid, and its value is 1. Now we're actually decoding, multiply, and placing into the reservation station, right? And what's the, and for the second source, multiply reads its second register and places this entry for its second source. Is the second source ready? Yes. Tag, we don't care because the source is ready. What's the value? It's 2. Right? Now I give you an example of how you can actually decode an instruction and place it into the reservation station. So let's back up. Basically, we have these reservation stations that keep track of each instruction. And for each instruction, you have the readiness of the source, tag of the source, and the value of the source for each source. Let's look at the structure of the machine. And you have this for the multiplier as well. So we're going to have the ready bit, tag, value of the first source operand for the multiplier, ready bit, tag, and the value for the second source operand of the multiplier. And these are, at the end of the multiplier and the adder, we're going to assume something. This is the common data bus. Once the instruction executes, what it does is it broadcasts its value, the value that's produced after the functional unit, and it also broadcasts its tag. Right. And where does this go? Well, now things become complicated. And you'll see the complexity here. This tag and value get broadcast to the register file. It also gets broadcast to the reservation stations. Right? Why? When the instruction executes, it generates its value, which means that the value that's tagged with that tag is available. And any instruction that's waiting for that tag now compares the broadcast tag to its own tag, or thought another way, anywhere that you see this tag, you have a comparison logic that compares the tag to the broadcast tag. And if the tag matches, the value is captured in the value field, and the ready bit associated with that tag is set. Anywhere in the machine. Right. Here, 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 here. And if you have other functional units, there also. If you have a load functional unit, which we don't have here, you have a similar thing. Make sense? Now it's simple, right? Okay, now let's go through the working of this. And you can see the value and tag here. Even though I combined them here, basically they're broadcast that way. Here I'm assuming a single bus, but actually the example assumes multiple buses. So we're going to modify that a little bit. You could actually have multiple buses, right? You can see the disadvantage of that. If the adder and multiplier broadcast different values and tags in the same cycle, now you need to have many, many more comparators, right? Twice the number of comparators. Here we're kind of assuming that there's some arbitration logic. If both the adder and the multiplier completes in the same cycle, well, one of them waits for a while before broadcasting. Okay. So now you know the machinery to enable this. And hopefully you're able to draw what the machinery looks like for this tag broadcast. Well, let's take a look at how it works. So actually, I should put this cycle. OK. So in the first cycle, we figured out, on the 0th cycle, the register file looks like this. In the first cycle, that's fetch. The first instruction is fetched. The interesting part is really the second cycle, when multiply is being decoded, right? So what does it take to decode the multiply? We need to read the register alias table for the source values, register 1 and register 2. Allocate a reservation station entry for the multiply. Place the source values and tags and valid bits into that reservation station entry. Good. Now we have our sources in the reservation station, but we need to do one more thing, which is rename the destination register, right? At this point, we have multiply in the machine, and it's going to write to R3, which means that later instructions better not get R3's value from the register file. They'd better get it from that tag that's going to be broadcast out of reservation station A. Now register 3 is mapped to reservation station A, and we forgot about register 3. Any instruction that's going to source register 3 at this point, after this multiply, is going to get the tag A and wait for tag A. That's renaming, yes? Should. Oh, was it multiply? Did I screw it up? Yeah. Oh, OK. That's good. Thank you. I guess that will confuse it. In your mind, you can rename X to A also, but let's fix it. You're right. Where is this thing? Actually, this is an easy fix. That's right. Now that works, right? Although it's not consistent with the slides over there, but you guys are smart, so you'll figure it out. OK? I guess when you're designing a machine, don't put the multiply instruction into the adder reservation station. That's the, that's the lesson from this. Otherwise, you may not get the correct results, however out of order your machine can be. Okay? Okay, now we have x and y. Oh, wait. Did I get it right? No, I need to rename these things, right? If we want to be consistent with that. Yeah, I think what I'll do is I'll actually keep this. This is our multiplier. I'm going to make these names x, y, z, t. I make these a, b, c, d. Okay, much better. So we're going to rename this to x, right? We put multiply into reservation station entry x with the name x. And the tag of register 3 is now x. Okay, that's cycle 2. Now done. Multiply is renamed. Right. In the next cycle, if you look at this, the third cycle, now multiply can start execution, right? Is that true? Well, there's some logic that checks every cycle whether an instruction is ready, right? In this case, both of reservation station X's sources are ready, which means that it can go and execute in the multiplier. Now, if there were multiple instructions that had sources ready, somehow there needs to be logic that figures out which one should execute. Right? So we've woken up multiply in the next cycle because its sources are ready. And if there was another instruction that was also woken up, that was also awake, we need to somehow select between those instructions, arbitrate which instruction goes to the functional unit. We're not going to go into that complexity, but this complexity is present in out-of-order machines. Okay, in the next cycle, multiply starts executing. What is that? Basically, its value gets fed to the multiplier. And, of course, the multiply carries a, or, well, not a, x, which is its destination tag. Because once the value is produced, it's going to broadcast the destination tag, right? So x, and then this will be 1, and this will be 2. So you have 1 times 2 that will operate until, for a while, right? You're going to multiply 1 with 2 for 6 cycles. Okay. At the same time, we're talking about cycle 3 now. At the same time, we're decoding the third instruction, right? Second instruction, sorry. What is that? Add R5, R3, R4. Add into R5, R3, R4. We do the same thing, right? First, add source register values, R3, R4. What do? Basically copy each of the entries to a reservation station that we allocate for add, and I'd better allocate it from the adder. Yes, R3, 0, x, 3. First source, 0, tag is x. Value, again, we don't care, right? Yes, it is 3. We can put 3 over here, but we're not going to use it because register 3 is not valid, which means that this value is garbage for our purposes because the value is really going to come from reservation station X, the result of the reservation station entry, the result of the operation that's currently housed by reservation station X. Okay? So that's why we don't care about that value. And register 4, we read this entry, 1 squiggly 4. Okay? Now we read the sources. Now we're going to rename the destination register. Again, it's the same way. Add is going to write to R5. R5 becomes invalid. And we've allocated that to reservation station A. So R5 is renamed to A. The tag is A. Okay? Now we can go through this, I think, until the end. I'll stop at some point. Well, let me. Oh. I guess this is cycle 3. Let's go back to cycle 3. Okay, it's better to look at it here. If you look at cycle 3, we're also fetching the second add. So let's look at cycle 4. At cycle 4, this is still executing, right? This add cannot execute, right? Because one of its sources is not ready. So it'll stay in the reservation station, not executing, waiting for its sources. But now the next instruction at cycle 4 can be decoded because we moved this. We moved this first add out of the way. What is that next instruction? Add R7, add into R7, R2, R6. Add into R7, R2, R6. We do the same thing, right? R2, R6, read from the register file, or register alias table. They happen to be both valid. Allocate a reservation station entry. It's an adder, so we allocate reservation station B and copy the entries in R2 and R6. And these are easy, right? 1, squiggly, 2, 1, squiggly, 6. And rename the destination register. R7, it's not valid anymore for the purpose of later instructions. And its tag, the value is actually going to come from reservation station B. Make sense? Let's do the renaming quickly for the other instructions also. In the next cycle, I think cycle 5, 1, 2, yeah, it's 3, 4, 5, we're decoding the next instruction, right? Which is add into R10, R8, R9. R8, R9. We do the same thing. R8, R9. By the way, in that same cycle, this instruction starts executing, right? Because its sources are ready in parallel to the renaming of the next instruction, the instruction that's writing into R10. We're going to wake up and select this instruction that's at reservation station B. Right? Okay, how do we rename this? R8, R9. Again, we read R8 and R9, and they're available. And this is an add. 1 squiggly 8, 1 squiggly 9. And we rename destination register R10. It's not available anymore. And the value will come from reservation station C. Next cycle, I believe it's cycle 6, multiply is renamed, the next multiply. Multiply into R11. Let's take a look at what that is. R7, R10. Okay. The same thing. You read R7, R10. Well, none of them are available. 0B7, 0C10, right? 0B. Again, we don't care about 7 because it's not ready. We're waiting for this tag. 0C. Again, we don't care. Although it doesn't hurt to write it because you're going to capture the new value anyway. And R11 is renamed to Y because the value of R11 is going to come from the instruction that executes from the reservation station Y. Okay? And the next cycle, I think this is the last cycle where everything is renamed. And I'm going to, right here. We're going to fetch this add instruction. It's writing into R5. It's sourcing register values R5 and R11. Okay, let's take a look at what is R5 and R11. So none of the source values is ready. 0A5, 0Y11. Oh, this is add. Okay, 0A5, 0Y11. Again, we don't care about these because the values are really not ready. Okay, I think now we've renamed all of the instructions. Well, not yet, not yet. Add still needs to write it to its destination register, right? I'll get it. Yeah, go ahead. Did I make a mistake?
R5 should be ready, right? Because R5 takes 4 cycles.
R5 should be ready. That's a good question. Is it ready at this point? Let's take a look at this. It's not ready yet, right? Because R5 is actually waiting for R3, right? If you look at this. R5 is produced by that add that's dependent on the multiply. Yeah. I haven't gone through all of the execution, but it's not. Yeah. If it was not waiting for that, then it would have been then it wouldn't have been ready. According
R5 is the second one, right?
if you look
R5
at
is produced by the second instruction there, and it's consumed by the last instruction.
that's right, exactly.
So R5 is ready.
But look at multiply. R5, the add is waiting for R3. The first instruction produces R3.
Yeah,
The second instruction waits for that R3.
that's fine. But then you're talking about the last instruction waiting for R5, right?
That's right.
So by the time the last instruction starts execution, it's ready.
No, it's not right, because the first multiply takes 6 cycles, and the add needs to take 4 cycles.
Right.
Remember,
so
it's
by the time R11 is ready, then R5 is ready.
by the time R11 is ready, that I cannot tell, right? Probably not, that's not true also, because R11 is also dependent on other instructions, right? So follow this timeline. This is the timeline, right? Time on the x-axis and the instructions on the y-axis. If you follow the dependencies, you'll see that R5 is not ready. Okay. You see? Okay, good. Okay. So at this point, yeah, we're renaming R5, right? If you look at this, R5, the add is writing to R5. Basically, add is placed into the reservation station D, which means that R5 is not ready because add is writing to it, and its name has changed to D. Now, anything that sources R5 after this is going to get D as the tag. So it's going to wait for D. So we're going to have the correct linkage, right? Previously, anything that sourced R5 after this add instruction waited for A, which was the previous name of R5. Now we're changing the name of R5 to D. In a sense, there are 2 versions of R5 in the pipeline now. One is going to be produced by A, and the other is going to be produced by D. Make sense? But they're totally different values, of course. Okay, so I believe that's cycle. So that's the end of cycle 1, 2, 3, 4, 5, 6, right? If I can see my alignment, yes. All of the instructions should be decoded after 6 cycles. Okay, now let's take a look at what happens after cycle 7. If you look at cycle 7, it kind of looks like this. All 6 instructions are renamed, and I hope that it looks like exactly like what I have here. I guess this is how I test myself, huh? Hopefully, yeah, exactly. It looks like what we have here. And notice what happened to R5. As I told you, it's renamed twice. Right? And you got the correct linkages. Now, if you look at cycle 8, if you look at this diagram, this is where actually one instruction finally finishes. And that's the first instruction. That's the first multiply. So this multiply has been executing for 6 cycles, and it finally finishes. Now what does it do? It broadcasts its tag, which is x. It also broadcasts its value, which is 1 times 2, right? So this is what it broadcasts, x2. And any location in the machine that has that tag compares x to the tag associated with it. Basically, you have comparators in each register that compare the broadcast tag to the tag that's stored. And only one of them matches in this case. If you look at the register file, one of them is actually x. And the val bit is 0, which means that this register 3 is waiting for this tag to be broadcast. And because x matches, we set the val bit to 1 and change the value to the broadcast value, 2. That's how we capture the value. Similarly, we need to do it for everywhere in the machine that has tags. X is broadcast into these tags, none of them match. X is broadcast into these tags, and these tags, well, there's one match here, right? And this was the add that was waiting for the value of the multiply that we placed into reservation station A. So now its source value becomes ready. Its value is 2. Now in the next cycle, this add can execute, right? because we can determine that it's ready, both of its sources are ready, it wakes up, and we can select it. Make sense? And that's what exactly happens here in this picture. Now, interestingly, if you follow this example, there's something else that happens in the same cycle. This third instruction, third add, also completes execution. What is the third add? That's add R7, R2, R6. Basically, it's the add that we placed here. It just happens to complete execution. In the same cycle, this multiply is completing execution. Right? Which means that it's going to also broadcast it's going to broadcast its tag, which is B, and it's going to broadcast its value, which is 2 plus 6. Now, if you had a single data bus, single broadcast bus for the values and tags, only one of them can broadcast, right? Which we would probably pick multiply because it's the older one. Think about which one you would pick if you had limited resources. This is an example of resource contention if you had only a single broadcast bus. But we're going to assume that we have two. So I'm going to do some magic here, which is you have another bus coming out of the adder that also goes through every location in the machine that has a tag, that stores a tag. And that also compares the tag that's broadcast with the tag that's stored and captures the value if the tags match. Okay? But you can see that two buses are expensive, right? Because now you've doubled the number of comparators. Okay, let's broadcast it regardless. Because we don't want to do this arbitration, maybe. But that may not be the best choice. Okay, B is broadcast. Now B is broadcast into this with the second tag bus. And we see that one of the comparators match. So this value becomes ready. Register 7 becomes ready. And its value gets changed to 8, right? Because that's the value that's being broadcast. At the same time, B is broadcast to everywhere in the reservation stations. Well, there's a match here. So this becomes ready. And the value becomes 8. Captures the value. Is there any other B in the reservation stations? No. So none of the other locations capture the value. Now this instruction that was renamed to Y has one of its sources ready, but because the other one is not ready, it cannot execute in the next cycle. Right? So it'll still wait for the next source. And remember, that instruction was the second multiply. What happened was the second add into R7, executed, broadcast its value, made the first source of the second multiply available, but the second source of that second multiply is not yet available because it's dependent on that previous add. Okay? So that's what happens in cycle, I think that's cycle 9, right? That's at the end of cycle 9. And similarly, at the end of cycle 10, this instruction broadcasts, which is add into R10. Right? So how does that broadcast? I guess add into R10 is C. It broadcasts its value C. That's the next cycle. So we broadcast C, comma, 8 plus 9, 17. That gets broadcast. Who captures that C? Well, R10. Because that's, it has its tag, which is C. And this instruction also captures that value because it's waiting for C. And no other instruction captures anything. Now this instruction can execute in the next cycle. This multiply can finally execute because it did capture the value. Okay? Now this assumes forwarding, so you broadcast the value and the tag before you actually write to it. At the end of the execution, you broadcast it. Right? You could imagine doing it later also, but this is assuming aggressive forwarding. Okay? Any questions here? This is clear, right? How out-of-order execution operates. It's pretty simple, actually. The basic principles are simple. The difficulty is really in implementing it. How do you actually implement it and get your cycle time low? Because now we have a loop, right? If you look at this, you see a lot of loops probably. What is the loop? This broadcast loop. You're actually executing the instruction and also broadcasting. Do you also wake up the next instruction in the same cycle? Well, probably that's not a good idea, right? Because now you're lengthening the cycle. Then the question is, when do you broadcast your value? We did not really discuss this. But you'd better broadcast actually before you finish execution, right? If you want your dependent instruction to get the value by the time you finish execution. So I think I've not given you the full picture here, but what we want is when the value is available, the dependent instruction to execute right away, to be scheduled and execute to be scheduled right away. For that to happen, the tag broadcast needs to happen in the previous cycle, right? Before the value is available. So that you select the dependent instruction, and dependent instruction is ready to execute, and then the value is forwarded to the dependent instruction, right? So there's a subtlety, which I did not discuss. Which also means that tag and value are not broadcast in the same cycle, right? If you do broadcast them in the same cycle, then the dependent instruction needs to have one more cycle. Needs to wait one more cycle to execute. Okay? So it's good for you to think about these implementation issues. The way it's described so far, it's beautiful, but when you start implementing it, you need to have these forwarding paths if you do not want additional delays. This is essentially forwarding in an out-of-order machine, right? If you want to do that forwarding, you need to be able to provide, you need to be able to broadcast your tag before the value is available. Okay? Okay, so in the end, basically what we get is 20 cycles. And I'll leave you, I'm not going to go through all of these right now, but these are some of the things that will enable you to remember what's on the board. But hopefully you've taken notes. Okay. Okay. I'll let you do the same exercise with precise exceptions. What I've assumed here, it was not precise exceptions. If you look at this, we update the register file. Actually, look at this. We update the register file out of order, right? Writes are happening all over the place. It's not in order. Once you do it with precise exceptions, it's not that hard, actually. You basically do not update the register file until the instruction is the oldest. But if you have a future file, there's no problem, right? So basically what we've done is this is a future file. Make sense? This is our future file that captures the future state. We also have at the back end, if you want to support precise exceptions, I don't want to really get rid of this, but maybe I have to. Maybe I don't. In the back end, we have another register file, which is our architectural register file. And that architectural register file gets updated in order. So that's our future file. This gets updated whenever an instruction broadcasts tag and value. And we have this reorder buffer here. Whenever an instruction broadcasts tag and value, it also writes its value into the reorder buffer. So an instruction, remember the reorder buffer, it has its value. And it also has the destination register ID. And when the instruction is the oldest in the machine, then you update this architectural register file. An architectural register file is the same as what we discussed, R1 through R11, except it's updated in order. So for example, this multiply, the first multiply, updates R3 when it actually is done. It updates R3 with whatever value it produces, right? 2. And if you look at the architectural register file, it's always valid, right? Whenever there's a program executing, it's always valid because you always update it with the retired instruction because it's the architectural state. And you don't need tags here because you update that with the reorder buffer, right? When the instruction is the oldest, it updates the destination register. Okay? So that's what an existing machine looks like. Actually, this is very similar to the Pentium Pro design as well. Pentium Pro had this future register file as well as the architectural register file, as we discussed. Okay. So that's how precise exceptions work. Basically, the idea is, I'll give you a break after I finish the precise exceptions part. The idea is we use a reorder buffer to reorder instructions before committing them to the architectural state. And an instruction updates the register alias table, essentially a future file, when it completes execution. An instruction updates the architectural register file, or backend register file, when it's the oldest in the machine that has completed execution. Now we're back to this. Okay, let me go over this, and then we'll take a break. Basically, what we've done is we've linked the consumer of a value to the producer through register renaming by associating a tag with each data value. We buffered the instructions until they're ready in those buffers, reservation stations. We kept track of the readiness of source values of an instruction with all of these ready bits. Actually, we really kept the track of the readiness of every value in the machine, right? Value. It's not associated with an instruction necessarily, but you keep track of the readiness of it. You keep track of the readiness of every potential value in the machine. You don't keep track of the readiness of this one because that's the architectural state. And if instructions basically compare, or values, compare their source tags to the broadcast tag, and if there's a match, the value becomes ready. And when all source values of an instruction are ready, there's some logic here that checks whether all source of an instruction are actually ready. Then the instruction is woken up. And among all the woken up instructions, there's an arbiter here that selects the instruction that needs to go to the function unit in the next cycle. So basically, register renaming eliminated false dependencies, enabled linking of producer to consumers. Buffering enabled the pipeline to move for independent operations. Tag broadcast enabled communication between instructions. And wake up as select enables out-of-order dispatch. I guess I'll stop here, and we'll take a break for a few minutes. And then we'll look into how this is actually data flow. Now you've seen the fundamental principles of out-of-order execution, and even how it's implemented a little bit. If you think about it, what we've done here is we've dynamically built the data flow graph of a piece of the program, right? Is that clear to you guys? What we've done is really we've linked instructions to each other in a data flow manner. And what are the linkages? Well, these things are the linkages, right? These names of values, these names we assign to the values are actual linkages between instructions. Well, what is that linkage? That linkage in a data flow graph is actually the arcs between the nodes, right? If you think of nodes as instructions, and that's what, or nodes as operations, as we discussed in data flow earlier, you have these instructions, instruction as its sources, source values, and a destination. Well, I guess I don't have my program here, but I had a multiply. Oh, there it is. There's my program. Multiply R3, R1, R2. I had this multiply. It got R1 and R2 as its sources, and it produced R3. Well, R3 is X, right? And we have this add that sourced X, and that also sourced R4, which was available. So I'm going to call it R4. And it's actually produced R5, right? I'll call this R3, I guess. That's renamed to X. And it produced R5. I guess I'm not going to do a good job producing the entire data flow graph, but I'm not going to do that anyway. And R5 was renamed to, well, it wasn't D, right? Do you guys remember what it was? This was add. It was B, right? Before. Is that correct? No, it was A. Yes, thank you. Right. And this result went into, I guess we don't know what sourced R5, but let's take a look at this one. This add itself, it got R2 and R6 and produced R7. Well, I guess R2 was fed to add also, and R6 was fed to this add and produced R7, which was actually renamed to something, which is B. And we had this other add that took R8 and R9 and produced R10. If you look at that, that's also R8, R9, and produced R10, which was renamed to C, right? And then we had this multiply, took R7 and R10. Actually, it really took B and C and produced R11. So it really took this and this, multiplied and produced R11, which was renamed to Y, right? And finally, we had this add that took R5 and R11. It really took, not D, of course. It really took whatever R5 was renamed at that point in time, which is A, and R11, Y. Well, I guess we did produce the data flow graph in the end. And then it produced whatever this was, R5, which was renamed to D. So that's the data flow graph. And if you look at this, you can kind of construct this data flow graph, right? Actually, you can construct this data flow graph because you know by looking at this, you know all the linkages in the machine. And that's what the out-of-order machine did. The data flow graph is present there in some other form. Not in this visual form, but in some other form. OK, which piece does it construct? Well, the data flow graph is limited to the instruction window, right? Basically, only those instructions that are renamed but not yet retired are part of the data flow graph that the machine is looking at. So the machine has a window. It looks ahead in the instruction stream. And that look ahead is limited to whatever you can store here. But it's pretty powerful. We didn't have this before. Now we have this data flow graph. If you have maybe 1 million entries, you can actually have 1 million of these nodes in your machine. Maybe we can actually get a data flow machine without programming it like data flow, right? This is all programming. This is all sequential instructions converted into data flow form. OK, and this is the definition of instruction window. Can we do it for the whole program? Yes? Well, if you have the entire machinery, maybe, right? And also, it may be tough to do it for the whole program because you need to have long latencies to be able to form the data flow graph in the meantime. Why would you like to? Or would you like to form a bigger window? Is there any reason for this? Some people say yes.
Depends on the IOP of the program.
The benefit that comes out of a bigger window, yes, depends on how many instructions you can execute in parallel, right? So here, for example, in this data flow graph, if you look at this, you know that you can start execution of these 3 instructions in parallel at the same time, right? So the benefit is good. Let's assume that you have that benefit. And in fact, many programs have lots of independent instructions. That's why out-of-order execution works. If you didn't have any independent instructions, if everything was serial, this wouldn't work, right? Because your data flow graph would look like, right? An out-of-order machine is useless in this case because there is no independent operation. But most programs actually look like this, and they do have this parallelism. But let's assume that they have this parallelism. Why would you like a bigger window? Why would you like to examine a much bigger window? Like, what determines the size of your window? That's what I'm getting at. Yes?
The size of how many reservations slots you have?
That's right, yes. That's how you build a large window. Well, how do you decide how large your window should be? How do you decide how many reservation stations you want to add? Yes?
How long are your dependent chains?
Or how long are your instruction latencies? Right? Maybe, for example, if your instruction latency is 2 cycles, maybe you don't need a huge window, right? Because instructions execute very quickly, and you don't even have time to fill the window. But if your instruction latencies are 500 cycles, when you get a load instruction, for example, it takes 500 cycles, and you have the ability to fetch 1 instruction per cycle, and if your window is only 10 instructions, well, guess what happens? You're going to fetch instructions for 10 cycles, and for the remaining 490 cycles, the machine is going to twiddle its thumbs. Wait. Yes?
Also, like, how many functional units you have?
That's right.
At
Yes.
some point, you need to do all the work, right?
That's right. You need to be able to execute those instructions. If you have only 1 functional unit that's always busy, that's not going to work. You're right. So yeah, as you increase the size of your window, you need to provide enough resources to be able to execute the instructions. But the reason you would like to increase the size of your window is really this latency. If your minimum latency is 1 cycle, there's really no need for an out-of-order machine. If your maximum latency is 1 cycle, there's no real need for an out-of-order machine, right? Because everything will complete quickly. I mean, you still need some buffering if you're fetching instructions in parallel. But that's different, right? That's not coming from out-of-order execution. That's coming from because you're fetching multiple instructions. Basically, your window size, you would like to be able to, if your load instruction misses are common, and if it takes 500 cycles, and if you're actually fetching, let's say, I don't know, 8 instructions per cycle, now your buffering needs to be even bigger, right? If you never want to stall on a load, you may want to buffer 4,000 instructions. That ensures that you don't stall. Maybe that's too aggressive, but think about building a machine with 4,000 instructions. That's a lot of comparators, right? And think about if you have multiple functional units, you do want to have these multiple buses, because otherwise you would be arbitrating between functional units that are broadcasting at the same time. And these buses, as the width of your machine increases, the number of comparators again increases, right? So the number of comparators are actually proportional to, if you have this issue with how wide your machine is, let's call it width, and also the depth, let's say. Depth is really the instruction window size. How many comparators you have is really proportional to width times depth. The instruction window size times issue width. So it's really significant. So it's hard to build a machine that has a very large instruction window. And this becomes, we'll get back to this. We do have this kind of latencies today, especially when we go to memory. And that's where we want to actually look ahead and figure out what instructions are independent so that we can do work while we're waiting for a memory access. So we do want large instruction windows, but we don't want to build them. So we'll get back to this. OK, how can we have a large instruction window? And I'll let you ponder about, can we do it efficiently with the algorithm that I described here? And with the power constraints, think about exercising this comparator, exercising, I don't know, 4,000 comparators, 4,000 times X comparators every cycle. That's a lot. So we really want efficient ways of implementing this if we wanted out-of-order execution. And people actually optimize this significantly. I'll let you read some of the papers. But it's beyond this course at this point. And if you're interested, I'd be happy to talk about it. OK, I think I've given you the data flow graph, so this is for you. If you look at the state of the register alias table and reservation stations in cycle 7, you'll get this. And you should be able to reconstruct this data flow graph that I reconstructed over here, which should hopefully be the same as this one. Kind of looks the same, right? Good, I guess I pass. OK. So this is essentially restricted data flow. An out-of-order machine is a restricted data flow machine. It's data flow-based execution, but it's restricted to the microarchitecture level. And ISA is still based on von Neumann model. It's sequential execution. It's also restricted in the sense that the amount of the data flow graph is restricted to your instruction window. And we already talked about this. I think you'll study this. You know data flow much better. Oh, I think I have the same slide here. Okay, some questions to ponder. I think I've already given you the answers to this. I've gotten ahead of myself, but why is out-of-order execution beneficial? What if all operations take single cycle? Is it beneficial? No. Because out-of-order execution is really a latency tolerance mechanism. You tolerate the latency of long latency operations by executing independent instructions. It's no more than that. And if all your latency, if you have no latency to tolerate, you have nothing to gain. And what if an instruction takes 500 cycles? I think I've given you the answers. How large of an instruction do we need to continue decoding, never stalling? And what limits the latency tolerance scalability of Thomas Low's algorithm? Basically, how large you can build this active or instruction window, right? Which consists of everything that's needed to keep around instructions that are decoded but not yet retired. All of those structures, reservation stations, register alias table, the broadcast buses coming out of all functional units, the reorder buffer, the register file, ... Scheduling window. Scheduling window is another name given to the reservation stations. If you think about it, this is the window that you look at to schedule operations, which may actually be smaller than your reorder buffer. Right. Why? Your reorder buffer can be much bigger than all of the number of entries that you have in your reservation stations. Any guesses as to why? Because an instruction, when it completes, it goes into the reorder buffer, right? When it's done with execution. Which means that when an instruction is done with execution, you don't really need to keep it around in the reservation stations, right? Because it's already executed. It's already produced its value. Anybody who was dependent on it hopefully captured the value through the tag broadcast. That instruction is essentially done. You just need to retire it, commit it to the architectural state. That's why it needs to go to the reorder buffer, because it may not be the oldest instruction when it's done, right? So it sits in the reorder buffer until it becomes the oldest instruction. Which means that reorder buffer can contain many completed instructions, but not yet retired instructions. Whereas in the reservation stations, you only need to keep instructions that are waiting for execution, right? That are being decoded and not yet executed. Whereas reorder buffer, you need to keep instructions that are decoded but not yet retired. So reorder buffer looks at a much greater set of instructions. That's why it can be bigger. Yes?
So when would you reset the tags?
When would you reset the tags? Oh, that's a good question. Basically, one way of resetting the tags is when the instruction actually completes execution. Right? When the instruction broadcasts its tag, what you also do is you deallocate the reservation station entry and then put the instruction to the reorder buffer because it's done at that point. You don't need to keep it around. Now, does that make sense?
So in your future file, you also need to have a link to the reorder buffer in case this is not valid.
No, if it's not valid, it must be sitting here. The instruction that's producing it must be sitting here. When an instruction completes execution, that tag becomes valid at that point, and that's broadcast. And that instruction can go into the reorder buffer. Okay. Let's see. Yeah, registers versus memory. This is always a good question. We've always talked about registers now, right? I don't even have a load or store here. And you remember that, well, we've considered register-based value communication. But instructions communicate through memory as well. And remember that I was going to ask you this question? We did have time to come to this question, which is nice. So what are the three differences? Three fundamental differences between registers and memory. We covered this in the last lecture. Anything? You're going to speak almost, but thinking. When are the values available? Or when are the dependencies known? That's one fundamental difference, right? Who knows the dependencies? The compiler knows the register dependencies, but the compiler doesn't know the memory dependencies, right? That's the first thing. Which one is bigger? Well, register state is small. Memory is huge, right? Well, because register state is small, we can rename it nicely, right? If the register space was huge, then renaming would be a little bit difficult. In fact, Intel Itanium, the first version of the Itanium, which is the first implementation of IA64, it has large register files. It was a VLIW machine, but people tried to implement it out of order also, because that latency, they figured out the variable load latency was a problem in their machine. And they wanted to tolerate it with out of order execution. So they wanted to execute these VLIW operations out of order. But their register file was very large. Their architectural registers, I think they had 128 architectural registers. And this was one of the limiters in their renaming. Okay, register state is small, memory state is large. And the last thing, which was important for us in the last lecture, register state is not visible to other threads or processors, right? Whereas memory state is visible to other threads and processors. Which means that we don't want to update this memory state speculatively. Whereas registers, we've been updating it speculatively. And that's the idea of the future register file, right? Whereas memory, we would like to update it when we know that the result is actually going to be committed. Okay. So in out-of-order execution, we need to obey memory dependencies also. We're obeying register dependencies. We're communicating, linking a producer of a register value to the consumer of a register value. How do we do that for memory? Now, memory is harder because we cannot rename, even if we were able to rename, let's say. When an instruction is decoded, we cannot say, oh, this memory location is going to be produced by this instruction, right? Because we don't even know that address of the memory location. We need to be able to execute that instruction to get that address. If we knew that address, you could potentially think of treating memory just like registers, right? Except with the difference that memory is huge. But we still need to obey these dependencies. We don't want to execute things out of order and have things get wrong values. And of course, we need to do so while providing high performance. And that's where this becomes a problem. Well, what is the problem? Memory address is not known until a load or a store executes. That's also an observation, right? Which means that renaming memory address is difficult for this reason. There are many other problems, which is determining dependence or independence of loads and stores need to be handled after their execution. You cannot treat them like registers. And finally, when a load or store has its address ready, because we're doing out-of-order execution, there may be younger loads, or younger or older loads or stores with undetermined addresses in the machine. So the problem becomes more complicated. It doesn't mean that whenever you execute a load, you have its address, but you don't know the addresses of some older stores, right? Well, what do? That's why this has been another fascinating problem in out-of-order execution machines. What do you do in that case? Well, when do you schedule a load instruction in an out-of-order engine, basically? The problem is a younger load. Actually, there are other problems too, but this is the real dependence, flow dependence problem, which is read after write dependence, read after write dependence problem. You have a load, younger load. It's waiting for a store. You have the store, you have this load. This load generates its address. You figure out that it's loading from address A. But the store is still waiting to generate its address because it's this, the base register is not yet available because it's some other instruction is going to produce it. So you don't know the address of the store. You have an unknown address here. But you do know the address of the load, which is younger in instruction order. This is known as basically, what do you do with this load? Do you start executing it? Well, what if the store is going to write to address A? Or do you wait until the store is finished? Well, if you wait, what if there are many, many stores, right? And they all have unknown addresses. Now you're conservative, right? Because maybe in the end you'll figure out that this load was dependent on none of these stores. You waited for nothing. Right? Basically, you've destroyed your performance. You've serialized the execution. Does that make sense? This is known as the memory disambiguation problem, or I guess in more English terms, unknown address problem, which is probably a easier way of thinking about it. Stores have unknown addresses, and dependent loads or potentially dependent loads don't know that. There are three approaches which I will leave you with. One, you could be conservative. You could stall this load until all previous stores have computed their addresses, or even retired from the machine. That way you are sure that this load will not get the wrong value. But this is conservative. And it turns out this has terrible performance. You could be, on the other opposite end, you could be very aggressive. You could assume when you compute the address of the load, this load is independent of unknown address stores and schedule the load right away. This is aggressive. This has better performance, but it doesn't always work. And also, it doesn't always work in the sense that there will be some stores that are going to store to the same address. A small fraction, but in that case, you need to provide the logic to recover, right? And existing machines actually have that logic. And you could be intelligent, right, as always. Yes, right. And that's what existing machines actually do. You predict with a sophisticated predictor. Well, actually, when you're aggressive, you're predicting something, right? Your prediction is that this load is not going to depend on any of the stores. When you're conservative, you're predicting something also, but that amounts to not predicting also, because you're just waiting. When you're intelligent, you actually use some separate predictor and guess if the load is dependent on any of these unknown addresses, or maybe potentially if the load is dependent on any particular one of these stores. Now, one prediction you can make is the load dependent on any of the unknown address stores? Then you need to wait. If the answer is yes, then you need to wait all of those stores. Another more sophisticated prediction is, if the load is predicted to be dependent on any of the unknown address stores, which one is it? Is it this one, this one, this one? Now it sounds like we're linking the stores and loads together, right? But with a prediction mechanism. And that's the idea. Yeah, history is one way of doing it. In fact, if you read the Alpha 21-264 paper, it does something like this. It doesn't link the stores and loads, though. But we're going to start with this one in the next lecture. But this is actually, if these do not prevent the scalability of an out-of-order engine, this problem prevents the scalability significantly, because we'll see how complex this is. Think about, here we're checking the tags, right? But ordering the loads and stores, think about how to do this. You really would like to get the value produced by the store that writes latest to that particular address. And how do you do that? It's essentially a content addressable memory that compares the address of this load to the address of all of the previous stores. And if you want to build a machine that houses maybe 1,000 instructions, this logic becomes very hard to scale. Okay? We'll start from this next time. See you Wednesday.